Hello everyone. The title of this video is Modeling Exponential Growth and Decay. So in this video, I'm going to be going over examples that are taken directly from a free online textbook at openstacks.org. I'm in their Algebra and Trigonometry text, section 6.7, called Exponential and Logarithmic Models. And I'm under the heading Modeling Exponential Growth and Decay. And each example I do is either going to be an example from the reading or one of the try it problems from the reading or one of the exercises at the end of the section that's related to this particular objective. Now for these exercises, for the examples I'm going to be doing, we're going to be working with this kind of a function every single time. Y equals a sub 0, where a sub 0 is some number, some initial amount of a substance, times e to the kt. And they have a little box down here talking a bit more about it. Right? Y equals a sub 0 times e to the kt, where t is in time, time units. K is called the continuous growth rate or continuous decay rate, depending on if it's positive or negative. Remember E, right? E is the number E. It's 2.71828, so on, right? A sub 0 we'll see as the the y-intercept of the graph of this function, but it's also the initial amount of a substance. Right, when t equals 0 at the initial time, that's when you get the amount y equals a0. And y will represent the output, will represent the amount of the substance we're talking about after time t. And they go over the graphs of these, right? When k is positive, when that k, that continuous rate of growth, is positive, we have an increasing function, right? Thus the name growth model, right? And if that value of k is less than 0, we get a function that looks like this. And you see the amount of whatever is decreasing as time goes by, as time increases as you go to the right. So when k is negative, they call it the decay rate, the value of k, and it'll be a decreasing function. Okay. So we'll come, but we're using this model for every single one of the problems in this video. Right. So the first one I'd like to do is actually example 1 from the text. Right, so let's take a look at that. So example 1, and I'm not going to do the solution. You can check the solution on your own, but obviously I'll show you the solution as I write it out. So here, graphing exponential growth. So here it says, a population of bacteria doubles every hour. If the culture started with 10 bacteria, graph the population as a function of time. So we have to model this. We have to fill in the relevant information to complete this model. And to complete this model, you need to know the value of a0 and k. Right, and I'll write this out. Right, I'll write this out. Now I'll do it so that you can still see the problem here. All right, you can still see the words from the example, and hopefully you can see my writing as well. But the model we're using every single time is y equals a sub 0 times e to the kt. And to complete the model and be able to answer any question that they have, to complete the model, you just need to find a sub 0, find that initial amount, the amount at time 0, and that k, which is called, again, the growth rate or decay rate, if it's positive or negative. Alright, so what, I'll just write out the relevant information, make the paper bigger. Yeah, we're using this every single time in this video. Alright, now they told us that this culture started with 10 bacteria. That means when t equals 0, y equals 10. Sorry, I don't know why I wrote 10 here. Sorry. Started with means t equals 0. T represents time. And this is time in hours here. Right? They said the bacteria doubles every hour. So you gotta pay attention to that stuff. What are the time units? And I can use this to find A0 really quickly, right? We have 10 on the left side for y equals A sub 0 times e to the 0 times k. Right? I replace t with 0 and the amount of bacteria with 10. Right? Y is the amount of bacteria here. And the right side is just a sub 0, because remember, anything to the 0 power, e to the 0 is going to be 1. So then I have a0 equals 10. That's, again, the initial amount. Very often you don't have to do all this writing. If they tell you the amount that's being started with, that's the a sub 0. All right. So now the model looks like this. Y equals 10 times e to the kt power. All right, now all that's left is to find k. And that's where the other bit of information comes in. Right? The only other thing we were told was that the population doubles every hour. Right? That other bit of information was that the population, the amount of bacteria, doubles each hour. So that gives us actually a lot of different pieces, a lot of different pairs of values for t and y. But this means, when t equals 1, right, 1 hour later, the value of y would be 20, wouldn't it? Because when you started off, when t was 0, y was 10. The amount of bacteria was 10. So 1 hour later, when t is 1, the value of y should double. Right? So 10 becomes 20. And we could do all sorts of stuff, other points. When t equals 2, the value of y would be 40. Right? 1 hour later, the population doubles. When t equals 3, the value of y would be 80. And I could do this forever. Right? I could do this all day long, get all sorts of ordered pairs of t and y. But I only need one of these. I only need one of these to find k, so I'm going to use this first one. So I replace t with 1 and y with 20, and then we'll solve for k. So I have 20 on the left, right, that's replacing y, equals 10 times e to the kt, but t is 1, so it's just e to the k. And then I solve this for k, and you should know how to solve such an exponential equation. I would divide both sides by 10 to have 2 on the left now equals e to the k. Remember, you get that base and power alone. Then we change to exponential form, logarithmic form. So k would be the natural log, the log base e of 2. And here's the value of k. So now I have the model complete. The a sub 0 is 10, and k is the natural log of 2. So I'll put those in. So now the completed model. The completed model looks like this. Y equals 10 was a sub 0 times e to the k, right, which is the natural log of 2 times t. Right. And this is great. All right, this is great right here. You can leave it this way if you wish. You can also, I've seen people do this plenty, round the value of k, but go out to at least 4 or 5 decimal places. All right, go out to at least 4 or 5 decimal places. So what is the natural log of 2? So I'm going to go to my desmos.com, free online graphing calculator here. Just punch in the natural log of 2. I'm going to go out to 4 decimal places, round to the nearest 10,000th, 0.6931. So I've seen people do this as well. I don't particularly like doing this, but we could also do this. We say y equals 10 times e to the natural log of 2. Now the natural log of 2 is approximately 0.6931 if I round to 4 decimal places. So 0.6931 times t power. This is also fine, but I would call this more of an approximate version. Here's an exact model because I didn't do any rounding. Here's an approximate model where we'll get values that are close, very, very, very close to the actual thing. Now, something else I like to do is I like to rewrite this using some properties of logarithms and exponents to get rid of the e in the natural log. Let me show you. There's nothing wrong with any of these. These are fine. So I'll say or. We have this, y equals 10 times e to the natural log of 2 times t. But remember, you can use the power rule for logarithms on this expression here. Because I have the natural log of something and then it's being multiplied by an expression, I can use the power rule for logarithms here, and then it looks like this. This would be 10 times e, and then I put that thing that's being the log is being multiplied by, I put that in as a power. This would be the natural log of 2 to the t power. And then this expression here, remember, e to the natural log of something is just that thing, right? Remember the inverse properties for logarithms. This is going back to earlier in chapter 6. I can use one of the inverse properties of logarithms now because I have a base raised to the log with that same base of some expression and be left with that expression. Use one of the inverse properties here, and I get this finally, y equals 10 times, and then e to the natural log of 2 to the t would just be 2 to the t. And this is something I would prefer to draw. But all 3 of these are equally valid. Right? All 3 of these are totally fine. It depends on what you prefer. Right, so 10 times e to the natural log of 2 times t power, or approximate that natural log of 2, right? Approximate the value of k, y equals 10 times e to the 0.6931 times t power, or using some properties of logarithms and exponents, we can get rid of the e in natural log and write y equals 10 times 2 to the t. All right, and then back in the example, we're asked to graph the population as a function of time. Well, I already plotted a bunch of points here. When t is 1, y should be 20. When t is 2, y should be 40. When t is 3, y should be 80. When t is 0, y should be 10. So if I'm plotting this graph on the coordinate plane, I already have a bunch of points to plot. Right? Now, be careful, the horizontal axis this time is now time. It's the t-axis in hours. All right, and the y-axis is the amount of bacteria. And maybe you'll want to label that. So you have 0, 10. All right, 0, 10, 120. 1 hour later, the population's 20, and then and I'll just do 40 here, go by tens on the y-axis. 2 hours, an hour later it's doubled to 40, and it should be this, increasing exponential function like that. Now notice I didn't go this way. I mean, you could, but that would be going like backwards in time. I'm going to make it like dotted because it really doesn't belong there. How can you go back in time? You can't, right? But starting off with 10 bacteria, then this is how the population of the bacteria increases based on this model, y equals 10 times 2 to the t. Right, and of course we can go to the Desmos calculator, look at a much nicer looking drawing. So I'll put it in the way I had it originally, y equals 10 times e raised to the natural log of 2 times t, right, and there you go. And you see it has 0, 10 on it, right? It has 120, or at least it should, right? 120. It has all those points I pointed out earlier. And like I said, you can put in y equals 10 times e raised to the 0.6931 times t power. And it's not exactly the same, but it's pretty much the same graph. See, if I turn it off and on, it's pretty much the same thing. But that's why I'm saying round the value of k to at least 4 or 5 decimal places to make it as accurate as possible. Or, as I mentioned, we can get rid of the e in natural log and write this as 10 times 2 to the t. And you see that's definitely exactly the same graph as the first one I drew. It's right on top of it. If I get rid of this one, see, it's exactly the same as that first graph. But either one's fine. Really, either one is fine. Okay, so that was example 1. Right? Use the information you're given to find, again, to complete these models and then be able to answer whatever question they want. You need to find that value of a0, this constant in front of the e to the kt, and then you also need to find the value of k using bits of information that are given to you. All right. Okay, so the next example I want to do is just the next example in the reading. All right, example 2 from the text. So let's take a look. All right, so first I'll clear these away. All right, and they talk about half-life here. So I'll explain half-life in a little bit because I'm pretty sure it's going to come up here in example 2. So it's about radioactive decay, right? You have a radioactive isotope that eventually decays into some other element like lead or something. Again, this isn't a chemistry lesson, right? But this may help if you have a chemistry class that talks about half-life or physics or whatever. So here, the half-life of carbon-14 is 5,730 years. Express the amount of carbon-14 remaining as a function of time t. Alright, so here we're not given some initial amount, so we're not going to be able to find a sub 0. We'll just leave it as a sub 0. But when they say half-life, right, when they say half-life, this is the amount of time it takes for a substance to decay to half its original amount. This is the amount of time it takes to decay, right, or for the amount to decrease, right, decay, to half the original amount. Alright, so they're saying here, the half-life of carbon-14 is 5,730 years. Right, so now my time is going to be in years. Now the model we're using is still the same model, right? Y equals a sub 0 times e to the kt, but this time we're only going to be able to find k, find the value of that decay, that continuous decay rate. A sub 0 is not given. They don't even give us any amounts of carbon-14 at all, right? They just tell us to write a model. So the only thing we can do is find K using this information. Now remember, what this means is that when T equals 5,730, right, when 5,730 years have passed, Y is half the original amount, so half A sub 0. I hope that makes sense, right? Because again, A sub 0 is the amount when time is 0. So after 5,730 years, Y, or the amount of carbon-14, is half the initial amount. And I mean, we could keep going with this. 5,730 years later, so that'd be 10,000 plus 1,400, 11,460. The amount of carbon-14 will be half of this amount. So half of a half, or a quarter, of the A sub 0. Like I said, you could keep going like this all day long. But I only need one piece of information to help me find K. Right? That's this piece here. So I'm going to replace T with 5,730 and replace Y with half of A0. So I have half of A0 on the left equals A sub 0 on the right times e to the 5,730 K. And then we solve for K. So first I would divide by A0. Now I hope you see that when I do that, the A0s would cancel on both sides, and I'd have 1/2, or 0.5 if you want to write that, equals e to the 5,730 times K, not T, K. Then I changed, now I have, base to power alone, I changed to logarithmic form. So 5,730 K equals, the natural log of a half. I'll just put 0.5 this time. Right. And then I would divide by 5,730. Right. So the value of K is the natural log of a half divided by 5,730, which, like I was doing before, I'll round to at least 4 or 5 decimal places if you want. Right? You don't have to use the rounded version, but so the natural log of 1/2 divided by 5,730. Yeah, I'll go to 5 decimal places this time, but because the first 3 are 0, negative 0.00012. Right. So approximately negative 0.00012 is the value of K. So the model here, the model for a half-life problem using, involving carbon-14 is this: Y equals some initial amount of carbon-14 times e to the natural log of a half divided by 5,730 times T. Or I could do this: Y equals A sub 0 times e to the negative 0.00012 times T. And again, notice the value of K is negative, right? It will be a decay problem when this is negative. It's a growth problem when it's positive. Or take the T over 5,730, put it in as a power, and then get rid of the e in log using the inverse rule. And we have Y equals A sub 0 times, and then it would be 0.5 to the T over 5,730 power. either one of these is fine. I personally like this last one. I like the ones with when after I get rid of e and natural log. But all of these are totally valid. Every single one of them. Right. Okay, and then we could make a little graph here. I'm going to go back here and I'm going to put in a value just called capital A, and then they'll probably have me throw a slider in for that. So y equals, capital A times E. Sorry, I'm going to do the one without E. So 0.5 raised to the T over 5,730. And you know what? It's having me put a slider in for T. So I'm going to change T to X. So it only has me do a slider for A. So now X represents time. And then there. See, so if I started with one, say 1 gram. Okay, why is it doing this? Yeah, this should not be horizontal. Maybe I'll do this. Maybe I'll change it to like a... I don't know why this isn't exponential. Oh, wait a minute. No, it is. I'm sorry. It is exponential. But it just takes, it takes 5,730 on the x-axis to make it go down to half, right? So I'd have to go really far out there to get it to look, yeah, it would be a while before I even see this thing looking like an exponential function. Yeah, there you go. It is exponential. It's just, and if I change the initial amount to 7.9, change it to 10 or something, yeah. Maybe I'll even make this a higher amount. Maybe I'll make it like 1,000. Make the initial amount 1,000, just so we can actually see it here. See, so if the initial amount's 1,000, then you see about a little over 5,000 years later, it's half that, and then a little over 5,000 years later, it's a quarter of that. Yeah, so that was looking like a horizontal line because we were zoomed in real far. But yeah, this is definitely an exponential function that models the situation. All right. Okay, great. And that's all they wanted in example 2 was write this model, right? Find that value of k and put it into the model. We don't know A0. Okay. So next is my third example. On the third example, I just want to go over try it problem number 1 from the text. So let's take a look at that. Get rid of these. And then here's try it problem number 1. So here the half-life of plutonium-244 is 80 million years. So it would take 80 million years for plutonium-244 to, whatever amount you have, to reduce to half its amount, to decay to half its original amount. So find a function that gives the amount of plutonium-244 remaining as a function of time measured in years. So this is very similar. Very, very similar to the last one. And this time the half-life of plutonium, which is just Pu-244, is 80 million years. And again, the same model, and you're going to see it. It's going to come back being basically the same stuff as the last example. But y equals some initial amount, which again, we're not given any initial amount here again. So all we're going to need to do is find the value of k, right, times e to the kt. And we need to find k. Well, again, half-life means that, the initial amount is a sub 0, and then 80 million years later, right, when t equals 80 million, y, right, the amount of plutonium-244, would be half the original amount, half of A0. So very similar to the last time, but instead of 5,730, it's 80 million. So all the same stuff would happen here. We have half of A0 equals A0 times E to the 80 million times K. And then we solve for K. So I'm hoping you can see that K would be the natural log of a half divided by 80 million. And this is really the case for any of these half-life problems. It's the value of K is just going to be the natural log of half divided by the half-life. Right, you saw that in the last example. K was the natural log of a half divided by 5,730. Here it's natural log of a half divided by 80 million, which would be incredibly tiny. So I'm just going to leave this the way it is. Now when I punch this in, so we got y equals a sub 0 times e to the natural log of a half divided by 80 million times t, and then you can take this t over 80 million and put it in as a power and get rid of the e in the log. So y equals the initial amount, a sub 0, times and then 1/2 to the t over 80 million power. And again, this is very much going to be the case for any half-life problem. Any half-life problem, this will be the case where you have y equals the initial amount times 1/2 to the t over the half-life. Right, last time it was t over 5,730, this time it's t over 80 million. But that is the case for all these half-life problems, radioactive decay problems. This will always be the way the model looks. All right. So that's it for that try it problem. Then the next example I want to do is the very next example in the reading, example 3. So let's take a look at that. So they're talking about dating, radiocarbon dating, right? How do they know certain things are the age that they are, right? Like fossils and stuff. So they give me an example here, a little how-to. So like here, finding the age of a bone using radiocarbon dating, right, which is about the amount of carbon-14. Now, remember they mentioned the half-life of carbon-14 is 5,730 years, right? That's brought up here as well. Right? 5,730 you're seeing all over the place. Right? Okay, so a bone fragment is found that contains 20% of its original carbon-14. So to the nearest year, how old is this bone? Right. So remember the half-life, I'll write half-life of carbon again, carbon-14. The half-life of carbon-14 is 5,730 years. And remember, we had our model from before. This is the model from example 2. Y equals, and it was some initial amount times e to the natural log of a half divided by 5,730 times t power, or y equals, some initial amount of carbon times 0.5, right, after simplifying this with properties of logs and exponents, to the t over 5,730 power. Okay. And y is, y is the amount of carbon, a sub 0 is the initial amount of carbon, right, 14, and then t is the time in years since that initial amount, right, since the death of the animal or whatever, right, since it started decaying. So they say this fragment, right, this bone fragment they know for some reason, they know that it contains 20% of its original amount of carbon-14. C14, carbon-14. So that means, right, this means that Y equals, right, the amount of carbon, that's the Y. The amount of carbon-14 left in the object is 20% of its original amount, so 0.2, that's 20%, times the initial amount, times A sub 0. Right. So I pop that in here, so we have 0.2, 20% of the initial amount of carbon is all that's left, equals A sub 0 times 0.5 to the T over 5,730 power. And then we solve this for T, and that'll tell us how old the thing is. All right, and they asked us to round to the nearest year. All right, so here I'm solving for T. We divide both sides by A0. And now I have 0.2 equals, 1/2 to the T over 5,730 power. And then I can change this to log form. Right, so T divided by 5,730 is equal to the log base 0.5 of 0.2. Now, if you don't like this, you can use the change of base formula, change it to like natural logs, do the natural log of 0.2 divided by the natural log of 0.5, and then I would just multiply by 5,730. Right? So we have T, and that would put that 5,730 in the numerator with the natural log of 0.02. So 5,730 times the natural log of 0.2 divided by the natural log of 0.5, and we're going to round this to the nearest year. This is how long it took for that to happen, how old the object is, or how long it's been decaying for. Right? So on the calculator, I've got 5,730 times the natural log of 0.2 divided by the natural log of 0.5. So this bone has been decaying for almost 13,305 years. If you're rounding to the nearest year, approximately 13,305 years, right, rounding to the nearest year. That's how long this bone has been decaying for, how long this animal who had this bone has been deceased. Right. Again, the key is to know the model, and we set this model up back in example 2, right? So I'm just using that and the information they gave to find the time, right? Find how long that thing has been decaying for. All right, now back in the textbook, you see they're showing you it's 13,301 years, plus or minus 1%. The reason why they're doing this plus or minus 1% is if you see the solution here, they're rounding. See how they took the natural log of the percentage that's left to 0.2? Right, we had natural log of 0.2 in our numerator, but then you see it's divided by negative 0.000121. So you see they took that natural log of a half divided by 5730 and rounded it, and that's why they're a little off of what we are. Okay, so just if you want to round to, if they tell you to round to 6 decimal places first and then do the calculation, then you can do it this way. But I personally like keeping things exact and not rounding till the very end, right? Even though they do the rounded thing up here. So if you want to do it their way, that's totally fine with the rounded version. I'm going to do it my way, though. I'm going to do it the exact way. Right. Great. All right, so next, I would like to do the try it number 2 problem. All right, so probably the one right after that. So it's the very same thing. So cesium 137, an isotope, a radioactive isotope of cesium, has a half-life of about 30 years. If we begin with 200 milligrams of cesium, so they're actually telling us, will it take more or less than 230 years until only 1 milligram remains? All right, so the half-life of cesium, I think that's CS137. I may be wrong. It's been a while since I've done periodic table junk. I guess I could look it up, but whatever. CS137, cesium-137 is 30 years, and about 30 years they said. So remember, the model for this would end up being y equals some initial amount times 0.5 to the t over 30. Remember, it would just be this model, but the denominator on the power is just the half-life. Now you could go through and find this model like I did in example 2. You can do that on your own if you wish, but I'm just going to jump right to the model here, telling me the amount of this substance is going to be some initial amount times 0.5, 1/2 to the t over 30 power, t over half-life power. Now they're telling us the initial amount, right? We are beginning with 200 milligrams. So a sub 0 equals 200, so that's going to make the model different, right? Y equals, instead of a0, now I have 200 there, times 0.5 to the t over 30 power. So here's the model I'm using now. And then the question was, will it take more or less than 230 years until only 1 milligram remains? Right? Now, we could do this, we know that when t equals 0, or I can make a table here, t and y. We know that when t equals 0, the amount is 200 milligrams. And then every 30 years, you get cut in half. Right? After 30, there's 100. After 60 years, there'd be 50 about left, Then 90 years, there'd be 25. And then 120 years, there'd be 12 and a half. Then 150 years, there'd be a 6.25, and so on. Now, until you get down to where you're below 1 milligram. All right. But even then, we won't be very accurate because they still have these gaps of 30 years. What if it happens between the 30-year marks? So basically, we're asking, when is y equal to 1 milligram, right? When is there 1 milligram left of cesium-137? So I just plug 1 in for y, solve for t. All right, so 1 on the left equals 200 times 0.5 to the t over 30 power. Now dividing by 200, 1 over 200 is the same thing as 5 thousandths, right? So dividing by 200 gives me 0.005, right? That's the same thing as 1 divided by 200. Equals, 0.5 to the t over 30. And then if you do log form and change a base to natural logs, you'd have t divided by 30 equals the natural log of 0.005, or 1/200th, divided by the natural log of a half. And then I'm multiplying by 30. All right, so t, the amount of time it takes for this 200 milligrams to decay to 1 milligram, would be 30 times the natural log of 1/200th, or 5 thousandths, divided by the natural log of a half. And rounding this, we'll round this to 1/10 of a year or something. Back on the calculator. So in the numerator, I have 30 times the natural log of 1/200th, divided by the natural log of a half. And it takes less than 230 years. This is 229 years, 229.3 years, which I've written down in my paper. Right, so it takes less than 230 years to decay to 1 milligram. And that's how we would answer that question. All right. Great. All right, and the next example I want to do are coming from the exercises at the end of the section related to this, exponential growth and decay model stuff. So exercises 28, 29, and 30 are all related. So let's go back to the text. And back all the way down to the bottom of the section here. To the exercises. Here we go. 28, 29, and 30. So here, under real world applications. So for the following exercises, use this scenario. A doctor prescribes 125 milligrams of a therapeutic drug that decays about 30% each hour. So every hour you cut it by 30%, so there'll be 70% left, from the previous hour. I'll use that fact. So to the nearest hour, what is the half-life of the drug? Okay. So again, we're using this model. Y equals, some initial amount times e to the kt. This is for any growth or decay. And we don't know the initial amount, right? We're not given, oh yeah, we are. Sorry. We are. The initial amount of this drug is 125 milligrams. And then it is mentioned that each hour drug decays by about 30%. Right, the drug decays by about 30% each hour. So that means, when t equals 0, y equals a0, right, whatever the initial amount is 125. And then 1 hour later, it gets cut by 30%. Well, if you cut out 30%, that means you have 70% left. I hope that makes sense. So 0.7 times a0. Again, I hope that's clear. If you decay by 30%, that means you have 70% left. All right, and then 1 hour later, all right, t equals 2, y would be 70% of this, so 0.7 squared times a0, and so on. Right? Right. But again, all we need is this piece of information right here to help us find k. Right? I know a sub 0. I just need this piece of information, one pair of values to find k. So on the y side, I put 0.7 times a0 equals, on the other side, a0 times e to the kt, but, t is just 1 hour. Right? Time is in hours here, don't forget. So I divide both sides by a0, that'll get rid of that, change to log form. So the value of k is the natural log of 0.7. Right? Which you could put in an approximation for if you want. But I'm just going to pop this in. So we have y equals, a sub 0, which is 125, times e to the natural log of 0.7 times t. And like I've been doing, put this t inside as the power on 0.7 and then undo the log and exponent with the inverse rule. This is 125 times and then 0.7 to the t. There's our model. This is the model we're going to be using. Y equals 125 times 0.7 to the t. I'm going to be using this model to answer their question. They want us to find the half-life of this drug. So basically when when the amount left is half the initial amount, half of 125, I'll just put it like this because we're going to see 125s canceling in a second anyway. What is t? What is the time? How many hours does it take to decay to half the initial amount? So I pop this in on the left side, half of 125 equals 125 times 0.7 to the t power. Okay, and then divide by 125. And you know what, I'm going to write 0.5, half as 0.5 again. Then we have 0.5 on the left equals 0.7 to the t on the right. So we see that t would be the natural log of 0.5 divided by the natural log of 0.7. Right? You can change to log form, then use the change of base formula, or take the natural log of both sides, pull the t out front, and then divide. And we're asked to round this to the nearest hour. All right, so this is calculator work. All right, so back here, the natural log of a half divided by the natural log of 0.7. So almost 2 hours. A little under 2 hours. If you're rounding to the nearest whole hour, right? So it's about 2 hours, right? It actually takes a little less than 2 hours, right? You saw 1.94 there. And you can see that here, when I was doing this, after 1 hour, you have 70% of the thing left. So 30% has decayed. After 2 hours, you'd have 49% left, right? 0.7 squared is 49%. So that means more than 50% has cut off, has decayed after 2 hours. So it would take a little less than 2 hours actually, but they're rounding it to 2 hours. All right, so that's exercise 28. All right, here's number 28. Find half-life. All right, then using the same model. Oh, well, gee, I already did this. So exercise 29. Write an exponential model representing the amount of the drug remaining in the patient's system after t hours. I have already done this. Then use the formula to find the amount of the drug that would remain in the patient's system after 3 hours to the nearest milligram. Right, so I've already done this. Right, this right here is the answer to number 29. That's the model we're using. And all they're asking now is how much, remember, y is the amount of drug left. T is the amount of time it's been running through the blood. T is the amount of time that's passed. And they're just asking how much of the drug would be remaining in the patient's system after 3 hours. So I just plug in 3 for T. Right. So after 3 hours, right, when T equals 3 hours, the amount of drug left would be 125 times 0.7 to the third power, which we're asked to round to the nearest milligram, right, the nearest whole number here. So back on the calculator, so 125 times 0.7 to the third power. So, and then to the nearest milligram, that would be 43. Right, approximately 43 milligrams left, after initially starting with 125. Pardon me. But it gets cut by 30% every hour. Right? So about 43 milligrams of drug are left in the patient's bloodstream after 3 hours. And that's it for 29. And again, so number 29 on that. And then number 30. So use the model found in the previous exercise. Find now f of 10. I didn't call it f of x, but you can call it f of t or whatever if you want. Basically, what's y when t is 10, right? The input, remember function notation. This number in the parentheses is the input, the time, and then f of 10 is the output, or the y value, right? The amount of drug left in the system, in the patient's system after 10 hours, right? When t equals 10 hours, it's the same stuff. Y equals 125 times 0.7 to the 10th. And we're asked to again round to the nearest, now this time to the nearest hundredth of a milligram. So I'm just changing this power up here to the 10th power. And then to the nearest hundredth, that'd be 3.53. So about 3.53, and then again that's milligrams. And they're saying, what does this mean? This means, there are 3.53 milligrams of the drug still present in the patient's system after 10 hours. That's what that means. All right. And again, you should have known that from basically how number 29 was asked, right? So here's the answer to number 30. Right? Wonderful. Right, so again, pretty simple stuff. Once you have the model down, though, right? Once you've established the model, you know A0, you know K, and you can rewrite it if you want. But once you know the model, have it completed, you should be able to answer any other question pretty easily. All right, I've got just one more example, one more set of exercises that are related. So exercises 38 and 39 from the text are also related to exponential growth and decay. So this time is about a growth, exponential growth of a population of bacteria. So for the following exercises, 38, 39, use this scenario. A biologist recorded a count of 360 bacteria present in a culture after 5 minutes. So time here is in minutes. And 1,000 bacteria present after 20. So to the nearest whole number, what was the initial population in the culture? And then we'll do 39 after that. But first I want to do a model, right? So again, all these exponential growth or decay models are the same. Y equals some initial amount times e to the kt power, or this time y is the amount of bacteria after t minutes, right? T is time in minutes this time. Now we're told when t equals 5, y, right, the amount of bacteria is 360. We're also told that when t equals 20, right, 20 minutes later, or after 20 minutes, the amount of bacteria is 1,000. Right, and I should be able to use this information to find a sub 0 and k. Right. So we'll get, what we're going to see here is actually a system of equations. We'll see two equations with two unknowns, a0 and k, and we can use it to find a0 and k. So here we have 360 equals a sub 0 times e to the 5k, right, like that. And then this one we have 1,000 for y equals a sub 0 times e to the 20k. That's a k, sorry. So, and now I'm looking at this system of equations, and we're going to solve this for a0 and k as well. All right. Now, honestly, I think solving for k would be easier here. Watch what I mean. All right. So in the first equation, see how a0 is 360 divided by e to the 5k. Right, if you were to divide both sides by e to the 5k. And then I can substitute this in the other equation. Right, so now the other equation becomes 1,000 equals, and then a sub 0 is 360 divided by e to the 5k, and then this is being multiplied by e to the 20k. And if you divide, use properties of exponents, this would be 360 times e to the 15k. Right? You subtract the powers on those because you're dividing things at the same base. And then I can solve this equation for k pretty easily. All right, divide both sides by 360. So you have 1,000 divided by 360 equals e to the 15k. And I'll reduce this number. This would be 100 over 36, which is 25 ninths. Right, that's 4 times 25. This is 4 times 9. All right, so e to the 15k equals 25 ninths. And then I change to log form, divide by 15. So k would be the natural log of 25 ninths divided by 15. All right, there's the value of k. All right, and now that I know the value of k, I can plug it in here and find a0. Right? So I'll go to another page for this. So we can find our initial amount now from this. A sub 0, remember from this equation up here, is 360 divided by e to the 5k, and we know k now. Is 360 divided by e to the 5k. Now 5 times k would make this denominator 3, so it's to the natural log of 25 ninths divided by 3. Right, that would be e to the, that's 5 times k. And then I put the 1/3 in as a power, and we can make that denominator there. Right, this is 360 divided by, and then just 25 ninths to the 1/3 power, or the cube root of 25 ninths. Again, that's put the 1/3 in as a power, and then do the inverse property. And I think we're asked to round to the nearest whole number. Right, so I'm going to punch this in my calculator and round to the nearest whole number of bacteria. So 360 divided by, and then 25 ninths raised to the 1/3 power. Right, so about 256 if I round to the nearest whole number. Right, so about 256 bacteria to start with. If there was 360 after 5 minutes and 1,000 after 20 minutes, right, the way it was growing. Okay, so now I have this model. Right, I know A0. So for right now, I'm going to use this for A0. You'll see why in a second, hopefully. You could also use 256 for the approximation, but we have y equals A0, which is 360 divided by 25 ninths to the 1/3 power. All right. Again, if you want to use 256, that's cool, but this is just the answer to part, exercise 38. They said what's to the nearest whole number, what's the initial amount of bacteria, 256. Now I can complete the model. Times e to that natural log of 25 ninths divided by 15 for k, right? Natural log of 25 ninths divided by 15 times t. And here's our model. Now again, I can rewrite this stuff in a lot of different ways. Here I'm going to take the t over 15, put it in as the power. Right, use the power rule, and then use the inverse rule. So I'm going to make this 360 divided by 25 ninths to the 1/3 power, and then this expression here, the e to whatever, becomes 25 ninths to the t over 15 power. And then I have something with a base of 25 ninths in the numerator, something with a base of 25 ninths in the denominator, then I subtract those powers. So my final model here is going to be y equals 360 times 25 ninths to the t over 15 minus 1/3 power. And that's all the exponents. So this is the model I'm going to use. Now again, you could also use y equals, 256 was the approximate initial amount from the answer to number 38, times e to the k power, right, kt power, and we can approximate this value of k here. I'll go to like 4 or 5 decimal places. It was the natural log of 25 ninths divided by 15. So 0.06811. Might as well go 5 there. 0.06811. And I'll use that, right? So y equals 256 times e to the 0.06811 t, right? And this is also good. All right, it should be good. And again, you can look at graphs of these and see that they're basically the same. All right, in fact, I will show you that. All right, let's graph these, both of these here. We have y equals 360 times 25/9 raised to the, and then we had t divided by 15 minus a third. Okay. And then the other one, y equals 256 times e to the 0.06811 t. Right. Now you can't see them because the initial value is at 256, way up here. See, there's 256 something, right? But you see they're basically the same graph. If I turn one off and on, they're right on top of each other pretty much. I mean, they're not exactly the same, but they look the same in a graph like this. So, I mean, they're approximately equal to each other. So either model you use is totally fine. Okay, so back to the assignment. So now we can use this to rounding number 39, rounding to 6 decimal places, write an exponential equation. Oh, so they went to, well, actually to 6 decimal places, 0.06811 would still be the value of k. So I already wrote that exponential equation. That was 256 times e to the 0.06811 t, right? And then to the nearest minute, how long did it take the population to double? How long did it take the population to double? All right, so the population to double. So remember, the initial population is about this here, right? In fact, I'm going to go back to this model. Right, this was A0. Right, this 360 divided by 25/9 to the 1/3. I'm going to call that A0, and then we have times 25/9 to the t over 15 power. I'm going to use that and say when is y equal to twice A0. Right, when is y equal to double the initial amount? When is the population doubled? So we have 2A0 for the y equals A0, right, A0 here, times 25/9 to the t over 15 power. Right. And then you can see the A0's canceling. I changed the log form. We have t over 15 equals the natural log of 2 divided by the natural log of 25/9. And then we just multiply by 15. Right? So the time it takes to double is 15 times the natural log of 2 divided by the natural log of 25/9. And it said to the nearest minute, right? And time was in minutes, so we're just going to be basically rounding to whole numbers here. So 15 times the natural log of 2 divided by the natural log of 25/9. So almost 10 minutes. So actually a little more than 10 minutes, but we're rounding to the nearest minute, and the nearest minute would be 10 minutes. So it takes approximately 10 minutes for the population to double. That's the answer to number 39. Now, say you use the other model. Right? If you use this other model, you'd end up with the time being the natural log of 2 divided by 0.06811. Right? You'd end up with this. If you were to put twice, 512 over here and then divide, you get 2, and then do the logs and all that. And hopefully this ends up to be about 10 minutes as well. Let me punch that in. So the natural log of 2 divided by 0.06811, and yeah, it's about 10.17 again. So it would round to 10 minutes. So however you did it, right, if you use the exact model I had, or this approximate model where you approximated the value of k and approximated the value of a0, either way you still end up with the same doubling time if you round to the nearest whole number. Right? It would still take about 10 minutes for the population to double, as it should. Right? They both should be about the same if they're the same model for the same situation. Okay, so that was a lot, but in every single one of them, we're using this. In every single one of them, we're using this model. The amount y equals some initial amount a0 times e to the kt. K is the growth rate if it's positive, it's the decay rate if it's negative. T is time, right? Time in minutes, time in hours, time in years, whatever. You just have to pay attention. And that was it, right? That was the key, knowing that this model was being used every single time. And we wanted to find a0 in a lot of cases. In most cases, though, we definitely wanted to find the value of k, right? And you should be able to do so using the given information. Sometimes it'll be a system, sometimes it'll just be a nice easy one-liner thing. But yeah, and I'm hoping that watching me do these 7 examples here help you out in some way when you're asked to model exponential growth or decay problems, radioactive decay, population growth, whatever, on your own. And thank you very much for watching.